In the next section, about section 8.2 graphs of polar equations, I want to talk about tests for symmetry. Back when we studied quadratic equations or other functions like cubic, quartic, that sort of thing, one of the things we talked about was symmetry, and graphs could be symmetric over the x-axis, the y-axis, the origin, the line y equals x. We said that graphs that were symmetric over the line y equals x were called inverses. And these graphs of these tests for symmetry, I guess you should say, is what will help you out with transformations of graphs, points, things like that. Now, for polar equations, the tests for symmetry change a little bit. They work the same. They change a little bit. We have three symmetric places. One of them is the polar axis. The polar axis was your x-axis. So to determine if a graph is symmetric over the polar axis, you're going to replace theta with negative theta. And if the two equations result in the same graph, then it's symmetric over the polar axis. If the graph completely changes, then it's not. The second thing we can check for symmetry over is the pole. The pole is your origin. So what we do is we're going to replace r with negative r. And again, if the two graphs, when you make the change, give you the same graph, then it's symmetric. If the graph is different, it's not. The last thing that we can check symmetry about is the vertical line theta is equal to pi over 2. That's your y-axis in essence. What you do is you replace theta with pi minus theta. And again, if they give you the same graph, it's symmetric. If they don't, it's not. Let's do a test for symmetry using the polar equation r equals 1 plus 2 cosine theta. I'm going to start with checking the polar axis. Remember I said if the graph is symmetric over the polar axis, then if I replace theta with negative theta, I should get the exact same graph. So what I want you to do is in your graphing calculator, I want you to graph the original graph, and then I want you to graph this. If they're the same, then it's symmetric. If they're not, then it's not. Now what I do is I just put into my graphing calculator the original graph. I look at it, and then I will graph on the same coordinate plane 1 plus 2 cosine negative theta. And if I only see one graph, then they must have been the same. And I only saw one graph, so I know it is symmetric over the polar axis. And then I check the pole. If I make this negative, and I get the same graph, then it's symmetric over the pole. Well, you have to do this first. Really, do you think that r equals negative 1 minus 2 cosine theta is going to give you the same graph? If you think it might, then just graph it in your calculator. Otherwise, you'd probably be able to tell it really quickly. It's not. So it's not symmetric over the pole. And then I check over the line theta equals pi over 2. So if r is equal to 1 plus 2 cosine of pi minus theta, and that gives you the same graph, then they're symmetric. And I graph them, and I see two distinct graphs. So it's not symmetric. And that's really all you have to do to check your symmetries. Do you really need to use those symmetries in order to help you graph? You don't need to. but it's a good way of looking at the graph to help you with how it's being graphed. Let's do a graph of r equals cosine of 2 pi over 3. This is one where we would definitely want to use our graphing calculator to look at the graph. But looking at a graph between 0 and 2 pi is not always the best way to see the entire graph. Sometimes you're only seeing part of the graph. So for the sake of argument, I want you to start in your graphing calculator by graphing the cosine of 2 theta divided by 3. And remember to hit zoom fit so you can actually see the entirety of the graph. And then you're going to see something that, I guess I did not see the entirety of the graph. Well, maybe I did. I guess I saw this. Looks something like this. But that's all I see between 0 and 2 pi. Maybe there's more to this graph if I continue to 4 pi or 6 pi or 8 pi. Well, how are you going to know how to change your window so you can see the entirety of the graph? Well, this is what I want you to do. Whatever the denominator is, if there's a fraction inside your sine or cosine, whatever the denominator is, I want you to multiply 2 pi by that number. So we're going to make our window for theta go between 0 and 6 pi rather than 0 and 2 pi. So if you hit the window button, you'll see theta min says 0 and theta max says 6.28. 6.28 is 2 pi. Just type in 6 pi and it'll change it for you. And then hit graph again. And you're going to see a lot more of this graph. You may have to hit zoom fit again so that you can see the entirety of the graph. Let's see what my calculator does. There it is. So now you kind of see that the graph does this other kind of like this. I'm not sure I'm doing it a lot of justice, but that doesn't look very good. Yeah, the picture on your calculator probably looks a lot better. Let's see, I'm going to try this again. It looks like it's got these little leaves inside, and then looks like it has these bigger, like that, right? Something like that. That looks a little bit better. Not great, but I like the picture on my calculator. It's very pretty. But in order to see the entire graph, we had to change our theta maximum. All you have to do is take the denominator of the fraction, multiply it by 2 pi, and that'll tell you what to change it to. And you'll get the best looking picture you can. I'm going to look at another equation real fast that you would need to put into your calculator in order to see its beauty. The graph of r equals sine theta plus sine cubed 5 pi over theta. In order to put into your calculator a trig function raised to a power, remember that we put the power here, but you're going to graph in your calculator this. It's going to look like this. You're going to raise the outside to the third. The calculator knows to do the sine of 5 theta over 2 and then cube it. So remember I said in order to see the entirety of the picture, if you have a fraction here, you're going to look at what the denominator is. And then you're going to multiply that by 2 pi. And this is going to give you the best viewing window. And you'll see this very pretty flower appear on your screen. It should look like figure 12 on page 551 of your book, if you did it correctly. The last thing that I want to look at is how changing the number being multiplied by the trig function changes the shape of the graph. This is a sine function, and so since it's a plus sign here, and it says 1 plus something times sine theta, the graph is going to be some circular shaped figure that's above the x-axis. If you start by plugging in 3 for C, you're going to get something that basically looks like this. Let's see, I'm not doing a very good job, but it's going to look kind of like that with a big loop in the middle. If you change C to 2.5, it makes the loop smaller. Try plugging in 2. It makes the loop even smaller. Plug in 1.5, it makes the loop smaller. When you get down to the value in front of sine being 1, you no longer have a loop. You have a dimple. So the ones with the loops inside, those are your limesons. The ones with the little dimples, those are your cardioids. And that was section 8.2.